Hello everyone, we are team 25072, and our senior design project is called Helium Recovery from Natural Gas. I'm Katherine O'Brien, and joining me are Ezra Harris, Lennon Shimsky, and Emma Walker. We are a team of chemical engineers, and over the next few minutes, we'll walk you through our design process, modeling efforts, and final recommendations for a helium recovery system that meets both our energy and purity goals. Here is our poster. This summarizes key information about our project and gives a process flow diagram of our simulation. And so, our project goal was to design a nitrogen rejection unit, or NRU for short, that recovers 96% of the helium in the feed. The system processes 50 million standard cubic feet per day of natural gas at a pressure of 800 pounds per inch gauge. So, the gas needs to meet pipeline composition standards of less than 2% nitrogen and be delivered at a pressure of 1,000 pounds per inch gauge. The helium product must be at least 65% by moles, and we also had to optimize energy use, which meant analyzing column pressures and comparing the use of turbo expanders to Joule-Thomson valves. So, helium is essential in industries like healthcare, electronics, and aerospace, but is becoming increasingly scarce. Helium is primarily obtained through extraction and natural gas processing, which makes projects like ours both economically and strategically important. As you can see in the graph here, global demand has been steadily increasing, making helium recovery systems very valuable. So, to make modeling feasible, we had to make several fundamental assumptions, including assuming ideal behavior for some of the lighter components. We based our inlet gas composition on data published by the Bureau of Mines in 1986 and used a sample from an Apache County, Arizona field. Our target outlet gas composition standards were set by the North American Energy Board, and we designed the system to operate at a steady state with negligible pressure drops outside of the core equipment. These allowed us to focus on the separation goals of our project, and we also, in addition to the assumption that all the acid gases have been removed before it enters our unit, and that the equipment is made out of 316 low-carbon stainless steel.
So this slide provides a high-level overview at what a typical natural gas plant layout looks like. In crude natural gases, there are basically three categories of components that need to be removed to prevent equipment damage and increase the heating value of the gas, and those are acid gases, which include CO2, water, and the inerts, which in this case are nitrogen and helium. So our nitrogen rejection unit handles this as the final step and fits into the broader system after gas sweetening and dehydration. In natural gas fields that contain nitrogen, it must be removed to boost the heating value of the gas and recover noble gases. Rejected gases can be either vented to the atmosphere or recycled for other uses. Cryogenic distillation, pressure swing adsorption, and membrane distillation are all methods to achieve this, and all are useful for different inlet compositions, target compositions, or throughputs. We ended up choosing cryogenic distillation because it's the most effective separation method for the scales we're working at. Distillation essentially works by taking a mixture of liquids and allowing the low pressure or the low boiling point liquids to boil off first, after which they can be condensed and collected. Cryogenic temperatures are required because all the substances we're working with are gases at room temperature and atmospheric pressure. Cooling is achieved through expanding the gases through either throttling control valves or turbo expanders. And this block flow diagram shows just a basic overview of our process. First, we have feed expansion, which cools the gas, initial separation in a high pressure column, and then a more complete separation in a low pressure column. And the nitrogen vent stream needs to be purified in a third distillation column. The hydrocarbon-rich waste stream or byproduct stream is recycled to increase the composition of all of our products. And then finally, there's product collection.
With that, here's our general process flow diagram. It takes you from the inlets to all our main outlets. We have a third column, which we talked about earlier, which is used to increase our helium recovery and our purity. The system includes turbo expanders to cool the gas prior to distillation and flash drums to pressurize the final product streams. The first column does the brunt of the separation work by separating the really light and heavy components. The second column separates the hydrocarbons from helium, and the third column separates the nitrogen from any leftover remaining hydrocarbons, which are then recycled back into our first column. However, this took a long time to get to this point. Here is our old model. Our old model was originally a simplistic two-column system, which readily hit every separation goal. Fortunately, though, with this system, we had an extremely high energy cost and was unable to successfully create a nitrogen stream that was able to be vented to the atmosphere without having high amounts of contaminants and pollutants. However, though, with our new model, as you see here, Compared to our earlier designs, our updated model reduces emissions, improves helium purity, and we've also optimized column pressures to reduce energy consumption while maintaining our required recovery and separations. However, though, to be able to fully explore this project, we did some economic and costing. A major part of this project was costing the equipment, labor, overhead, general expenses, utilities, and many other components to explore the economic feasibility of the system. Economically, as you see here, the system is extremely promising. As you can see, we have crude helium alone brings in over $107 million annually in sales. With only an initial startup cost of around $23 million, the system has a net profit of over $40 million annually, even after a tax rate of 25.9%. However, though, one of our largest costs from our system is the utilities. We calculate utilities for cooling, heating, and expansion, which are our three main systems. The three main utilities we used was a high-pressure steam to heat the three boilers, which are part of our distillation column, electricity for the pumps to move the liquids between the systems, and R290, which is just simply propane to act as a coolant to cool down our system. One of the big parts of this system was energy optimization. From this work, we found turbo expanders were far more efficient than Joule-Thomson valves, especially when considering the energy recovered from these internal turbines from these systems. As you can see there, we have an electric generation of 670 kilowatt hours being generated from our system.
Environmental compliance was crucial and one of the largest optimizations the team made this semester for our model. Our nitrogen vent, categorized as a miscellaneous vent by the EPA, originally exceeded methane limits. By redesigning the distillation sequence by adding a third column and the addition of a flash drum to increase the efficiency of the column, we cut methane emissions of 4.09 kilograms per day, well below the EPA threshold of 6.8 kilograms. This ensured our system was both profitable and compliant. Summarize, the nitrogen content in the pipeline meets pipeline specifications, and with the recycled stream, increased recovery of hydrocarbons through optimizations done this semester. Helium purity and recovery were beyond the design targets both this and last semester, as the team was trying to reach grade A helium standards, which is discussed in the next slide. The nitrogen stream is now vented safely with minimal hydrocarbon losses. These results meet and exceed all design targets. We recommend that future designs explore a broader range of inlet gas compositions to identify the most profitable feedstocks. We also suggest adding a PSA unit to further purify helium to grade A levels. The sales of crude versus grade A helium showcase the 4 times increase in profit if we were to reach this standard of helium. The team did explore a cryogenic PSA hybrid system with the PSA at the end, but with learning a different chemical engineering software, Aspen HYSYS, it brought on a bigger challenge than expected. We were already well above the constraint for helium purity, so we decided this was satisfactory for the time being. Thank you for your time. We'd like to thank our mentors, Dr. Adriana Brush and Melissa Young, for their guidance throughout this project.